In this video, we continue our discussion of boiling point elevation and freezing point depression. So we'll look at a couple of additional practice problems. And so say, for example, we have a 25% solution. This is a percent by mass solution of sodium chloride. And the first thing we're asked is the I value for this solution. So remember our I value, that's our Van't Hoff factor. It depends on if we have an electrolyte or a non-electrolyte. My sodium chloride, I've got that sodium there that's a metal. That tells me right away that that's an ionic compound. And if I have an ionic compound, this is an electrolyte. So my sodium chloride is composed of sodium cations and chloride anions. So when it breaks up, it produces 1, 2 ions. So that means my I value will be 2. So then we're asked to calculate the boiling point for this solution. So if we want boiling point, we need our temperature change being equal to K times M times I. Again, we're assuming this is an aqueous solution. So we have our K value. K is going to be 0.512 degrees C per molality. We just said that I is 2, and we're going to need our molality. And we're given this mass percent. So we've seen in a previous video an example of how to take that percentage and convert it to molality. In that example, we looked at doing that with ethylene glycol, a non-electrolyte. So here we're using the same concentration by mass, but we're looking at an electrolyte solution. So remember that that mass percent means that I have 25 grams of my solute, sodium chloride, present in 100 grams of my solution. And if my total is 100, 25 is my solute, that means that 75 will be my solvent. So for molality, that's going to be moles of our solute per kilogram of our solvent, so per kilogram of water. So using what we have in that mass percent, I'm going to take my 25 grams of sodium chloride, and I'm going to convert it to moles using the molar mass, which is 58.44 grams per mole, which is going to give me 0.428 moles of sodium chloride. So my molality is going to be my moles of sodium chloride divided by kilograms of solvent. So my solvent is the 75 grams of water. So converting 75 grams to kilograms is 0.075 kilograms, which gives me a molality of 5.71 molal. So my boiling point, next I can calculate my boiling point change. That temperature change will be equal to K, which is again 0.512 degrees C per molal, times our molality, times our I value. And this time our I value is 2, since that compound formula has 2 ions. So that's going to give me a temperature change of 5.84 degrees Celsius. So if I want my new boiling point, I have to take the original boiling point of water. I'm going to add my temperature change so that my new boiling point is 105.84 degrees Celsius. So on our worksheets, we had an example 3 in which we had a 25% ethylene glycol solution. And in that scenario, we had calculated our boiling point to be 102.75 degrees Celsius. So we're asked to compare these two solutions. We mentioned when we started talking about colligative properties that the more particles we have in solution, the greater impact it's going to have on our colligative property. If we compare our temperature change, we got a temperature change here of 5.84 degrees Celsius compared to the ethylene glycol of 2.75. We have almost double the change. But we certainly see that it's higher. So having more particles present in this solution, because we have an electrolyte, resulted in a greater change in our boiling point. Now next we're asked to calculate the freezing point and boiling point of a 5.5% solution by mass of aqueous sodium nitrate. We're doing the same kind of thing we saw in that previous problem. So that 5.5%, that means I have 5.5 grams of sodium nitrate, my solute, in 100 grams of my total solution. And then the remaining mass is my solvent. So the 100 minus 5.5 gives me 94.5 grams of water, which is my solvent. And I know water is my solvent because in this case we were specifically told it was an aqueous solution. So whether I'm calculating freezing points or boiling points, I'm going to find the temperature change through the concentration, and I need my concentration in molality. So to get that molality, I'm going to need moles of my solute divided by kilograms of my solvent. So I'm taking the 5.5 grams of sodium nitrate, I'm converting them to moles, using the sodium nitrate's molar mass, which is going to be 85 grams per mole, which is going to give me 0.065 moles of sodium nitrate. So my molality is going to be the 0.065 moles of my solute divided by kilograms of my solvent. So the solvent is the water. That's the 94.5 grams. Converted to kilograms would be 0.0945 kilograms. So that's going to give me a molality of 0.69. So whether I'm calculating freezing point or boiling point, I need the concentration. So we've got our concentration now of 0.69 molal. So now we can plug into our temperature change equations. So if I want freezing point, I'm going to plug in the freezing point depression constant for water, which is 1.86 degrees C per molal times the molality we just determined. And then we need our I value. So looking at this sodium nitrate, that is an ionic compound. It's got that sodium, which is a metal. Here we've got to be careful. That sodium nitrate, it breaks into Na plus and NO3 minus. So my polyatomic ion, that's a single unit. It doesn't break into nitrogen and oxygen. It stays together as the NO3 minus. So I have one particle from my sodium plus one from my nitrate. So that makes my I value 2. So I'm going to plug in a 2 for my I value. So that is going to give me a temperature change of 2.6 degrees Celsius. So this is freezing point depression. This is how my temperature decreased. So water freezes at 0. We are decreasing by 2.6 degrees Celsius. So my new freezing point is negative 2.6 degrees Celsius. Now, if we want boiling point, we're going to do the same thing. We're just plugging in a different constant. So we're still using the delta T equals K times M times I. But we're doing boiling point, so we're using the boiling point constant of 0.512 degrees C per molal times our molality of 0.69 times our I value of 2. And so this time we're going to get a temperature change of 0.71 degrees Celsius. And so when we're looking at boiling point, we start at 100 degrees. We increase by 0.71. So our new boiling point is 100.71 degrees Celsius. So for any solution, whether it's an electrolyte or non-electrolyte, as long as we know what that substance is, we can use its concentration to figure out the boiling point for our solution. Now, at the same time, it may be useful to use temperature changes to determine a concentration. We can measure temperature change very easily in the laboratory. So if we look, for example, at problem 12, we're told we've got a solution of citric acid in 50 grams of acetic acid, and it has a boiling point elevation of 1.76 degrees Celsius. And we're asked for the molality of our solution if the boiling point elevation constant is 3.07. So what we're going to do, we're being asked for molality. And we're given temperature change. So we know we have a relationship between molality and temperature change through the equation delta T equals K times M times I. So all we're going to do is plug in this information into our equation, and we're going to solve for our molality. So my temperature change was 1.76 degrees Celsius. My K, we're told, is 3.07 degrees Celsius per molal. We're looking for our molality. And then we look at that formula, C6H8O7, it's all nonmetals. And since it's all nonmetals, this is molecular. It's a non-electrolyte, so its I value is 1. So rearranging this to solve for my molality, we're going to have 1.76 degrees Celsius divided by 3.07 degrees Celsius per molal times 1. And we're going to get a molality of 0.573 molal. So if we know a temperature change, we can use that to find the concentration of our solution. Now that could be particularly useful if we're dealing with the solution of an unknown substance. So in our next video, we're going to take a look at that. We're going to use temperature change to find concentration, but we're going to then further use that concentration change in order to determine things like the molar mass for an unknown substance.